In the dark frontier of the cosmos, there are boundaries where matter is pushed to its ultimate limit. Places where gravity crushes atoms, time slows to a crawl, and the very laws of physics tremble on the brink of collapse. Among these boundaries stands one of nature's most extreme creations, the neutron star. But beyond that, deeper still lies a point of no return, the event horizon of a black hole. So, how close can a neutron star get to that edge before it's swallowed by gravity itself? What is the absolute limit of matter? To understand how compact a neutron star can become, we first have to understand where it comes from. It all begins with a massive star, at least 8 times the mass of our own Sun, for millions of years. It burns hydrogen and helium in a delicate dance between the inward crush of gravity and the outward push of nuclear fusion. But eventually the fuel runs out. When that happens, gravity wins. The star's core collapses in a fraction of a second. The pressure is so immense that it crushes protons and electrons together to form neutron particles so tightly packed that a single teaspoon of this material would weigh billions of tons here on Earth. What's left behind is a neutron star, a city-sized sphere, only about 20 kilometers across, but containing up to twice the mass of the Sun. Neutron stars are so compact they defy imagination. On their surface, gravity is over 200 billion times stronger than on Earth. Any mountain you tried to build would collapse under its own weight after rising just a few millimeters. Inside, the structure becomes even stranger. The outer crust is made of atomic nuclei crushed into dense crystalline lattice. Beneath that lies a sea of neutrons, a superfluid that flows without any friction and is unbelievably dense. And deeper still, at the very core, the pressure may be so intense that even neutrons begin to break apart. Some physicists believe that matter transitions into something even more exotic, perhaps quark matter, or even strange matter, where the fundamental building blocks of protons and neutrons, quarks, roam freely in a quantum soup. The more mass a neutron star packs on, the more gravity tries to crush it. But the internal pressure of something called neutron degeneracy, a powerful quantum mechanical effect, pushes back, resisting the collapse. At some point, though, gravity's pull becomes too strong. The neutrons can no longer support their own weight. This critical boundary, this cosmic tipping point between a neutron star and a black hole, is defined by the Tolman Oppenheimer-Volkoff limit, or the TOV limit. Named after the physicists who first calculated it back in 1939, the TOV limit represents the absolute maximum mass a neutron star can have before it must collapse under its own gravity. It's like a cosmic balancing act, gravity pulling in, neutron pressure pushing out. If the mass is below the limit, the pressure wins and the star remains stable. If it exceeds that limit, no known force in the universe can resist the final, crushing victory of gravity. But what is that limit exactly? Theoretical models suggest it lies somewhere between 2.1 and 2.3 times the mass of our Sun. The exact number, however, depends on something called the equation of state, the relationship between pressure and density inside that bizarre neutron star matter. Since we can't recreate these conditions on Earth, the true nature of this matter, and therefore the true value of the TOV limit, remains one of the biggest mysteries in astrophysics. Astronomers have been searching the cosmos for the most massive neutron stars, hoping to find one teetering on the very brink of collapse. In 2010, they found a neutron star called PSRJ 1614 to 2230, weighing in at a hefty 1.97 solar masses, already pushing the theoretical limit. Then, in 2019, a new record holder appeared, PSRJ 740 plus 6620, with a staggering mass of about 2.14 solar masses. These cosmic heavyweights challenge our understanding of matter under extreme conditions. The fact that such a star can even exist without collapsing tells us that the equation of state must be stiffer than we thought, meaning neutron matter resists compression more strongly than some models predicted. But what happens as a star gets even heavier as it creeps right up to that razor's edge? Imagine a neutron star in a binary system, siphoning matter from a companion star. As it gains mass, it grows denser. Its radius shrinks, its surface gravity skyrockets, and time itself on its surface begins to slow down relative to the rest of the universe. Just before reaching the TOV limit, the escape velocity from its surface approaches the speed of light. The curvature of spacetime becomes so extreme that light itself struggles to escape. It hasn't become a black hole yet, but it's right on the verge. At this point, even a tiny nudging increase in mass of just a few hundred thousandths of a solar mass can trigger the final, catastrophic collapse. When that threshold is crossed, gravity takes over completely. The neutron star implodes, collapsing inward faster than the speed of sound through its own matter. Within milliseconds, it forms a black hole, a region of spacetime so warped that nothing, not even light, can escape. For a brief, violent instant, the collapse may release a powerful burst of energy, perhaps as gamma rays or gravitational waves. Then, silence? A singularity is born, forever hidden behind an event horizon, and we've actually witnessed this happen. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger known as GW1 70817. When these two stars collided, their combined mass briefly exceeded the TOV limit. For a few milliseconds, they formed a hypermassive neutron star spinning incredibly fast, supported by both centrifugal force and intense thermal pressure, but that fragile balance couldn't last. Moments later, it collapsed into a black hole. This was the first direct confirmation of what theorists had predicted for decades. The line between neutron stars and black holes is razor-thin, and it can be crossed in a single violent instant. So how compact can a neutron star get before it gives in? Astrophysicists measure this with a simple ratio of mass to radius. For a black hole, this value is 0.5, the point where escape velocity equals the speed of light. A typical neutron star has a compactness of about 0.2. Simulations suggest that at a compactness of around 0.3 to 0.35, neutron star matter can no longer hold itself up. The core collapses and an event horizon forms. Nature allows no half measures. You can get incredibly close to the edge, but you can never hang out on the other side. Of course, things like rotation and magnetic fields complicate the picture. A fast-spinning neutron star, known as a pulsar, can support slightly more mass before collapsing because the centrifugal force helps counteract gravity. These effects are small, but near the TOV limit, even tiny differences can determine whether a star survives or is erased from the visible universe. On the other side of that boundary, scientists have searched for the lightest black holes, those born just past the collapse point. Finding one with a mass around 2.5 solar masses would mark the transition, the missing link, between neutron stars and black holes. And in 2019, the gravitational wave event GW1 90814 gave us a tantalizing clue. A mysterious object of 2.6 solar masses merging with a much larger black hole. Was it the heaviest neutron star ever recorded, or the lightest black hole ever found? We still don't know for sure. That object sits right in the mass gap, the very place where our physics becomes uncertain. To truly answer how compact a neutron star can get, we need to understand what happens inside its core at densities far beyond anything we can test on Earth. Here, physicists are turning to heavy ion colliders like those at CERN to smash atomic nuclei together and create tiny, fleeting glimpses of nuclear matter under extreme pressure. These experiments, combined with astrophysical data from missions like NICER on the International Space Station, are helping us map out the possibilities for how matter behaves when pushed to its ultimate limit. The line between neutron stars and black holes isn't just a boundary of matter. It's a boundary of our knowledge. Beyond it, our current physics breaks down. General relativity describes gravity, while quantum mechanics describes matter, and at this intersection, neither theory is complete. By studying neutron stars on the brink of collapse, we're not just looking at stars. We are testing the fabric of the universe itself, searching for clues to a unified theory of quantum gravity. So, how compact can a neutron star get before collapsing into a black hole? The answer, as far as we know, is about 2.3 times the mass of our Sun, packed into a sphere no larger than a city. Beyond that critical point, gravity's grip becomes absolute. At that moment, space folds in on itself, time stands still, and what was once a star filled with the memory of nuclear fire becomes a silent shadow in spacetime. The answer isn't just a number. It's a boundary between the known and the unknown, the visible and the invisible, the star and the singularity. Because at the edge of collapse, the universe whispers one final truth: not even light can escape gravity's final embrace. Thanks for joining us on this journey to the edge of physics. If you enjoyed this cosmic exploration, don't forget to like this video and subscribe for more deep dives into the mysteries of our universe. See you next time.